Hello everyone, welcome to this lecture. In this lecture, I am going to discuss full adder. Full adder is also a combinational circuit. That means it also does not have any memory element. In the previous lecture, I have discussed the half adder. There was a limitation. Half adder doesn't deal with the previously generated carry. So in case there is a number which is having, let's say, 1 1, and we are adding this with this number, there are two numbers. Okay, now if there is any carry generated out of here, so let's say this is 0 and there's a carry which is coming, the half adder doesn't deal with, or half adder is not capable to deal with this carry. That is the limitation, right? So to overcome such kind of limitation, full adder is there. So full adder can deal with it. So let's draw the truth table for full adder. Drawing it. Okay, so the truth table look like this. If you add these three bits, let's say 0 0 0, we all are aware about, it will give us sum as 0, and there will not be any carry output, so the C out will also be 0. There are two carries we are taking here, C in and C out. C in case any input carry is there, and C out when we are adding any output carry is being generated or not. Now if this is 0 0 1, when we add it, so altogether when we add 0 0, it will give us 0, and when we add the 0 with 1, it will give us 1. So sum we will get as 1 only, and there will not be any carry, so carry will be 0. Now same case is here, sum will be 1 and carry will be 0. Now here if we add it, so let's say when we add these two things, there will be 0 plus 1 will give us 1, and 1 plus 1 will give us 0. So the sum will be 0, but there will be one output carry, right? Now here there will be sum as 1 and there will not be any carry because there is only single one. But in this case, because there are two ones, the sum will be 0 and carry will be 1. Now here also sum will be 0 because there are two ones, carry will be 1. And in this case, when we add 1 1, it will give us, let's say, 1 0, so 1 carry and 0. And when that 0 will be added to 1, so sum will become 1, as well as we will get carry also. So this will be the truth table for the full adder. Now let's try to find out the Boolean function for sum as well as for carry output. So we can generate the Boolean function for sum with the help of K-map. So let's draw a 3 variable K-map where there will be 8 cells. So we will draw 8 cells K-map, 2 rows, and there will be 4 columns, right? Something like this. We have like A, B, and C in, right? So there are 2 rows and 4 columns. We can make this K-map like this. like this. Now it is like 0, A is 0, and here A is 1. This side both are 0, 0, 0, 1, 1, 1, 1, 0, right? So we are familiar how to draw the K-map. Now fill the values. So it is 0, 1, 0, 1. No, we are filling the value of sum. So it is 0, 1, 1, 0. So this is 0, 1, 1, 0, and 1, 0, 0, 1. So it is 1, 0, 0, 1. Now here, if you want to form the groups of these ones, you find out there is no such possibility that we can group or more than one. So let's say this is an individual group, this is an individual group, this is an individual group, this is an individual group. There is no possibility so that more than one can be combined. And such kind of arrangement we consider chessboard arrangement or checkboard arrangement. Whenever you get such kind of arrangement, you do remember that you will get the XOR of all the variables those are involved. So there are 3 variables involved, and this was the K-map for sum. So I'm writing here, this was the K-map for sum. So in case we write the Boolean expression for sum or S, whatever you say, the sum will give us A XOR B XOR C in. So please do remember such kind of K-map where there is no possible combination, or it is a checkboard kind of problem, checkboard situation. Okay. In that case, whatever the variables are involved, you just need to take the XOR all of them, and that will be the solution for that, right? So the Boolean expression we will find out for sum like this. Now if we talk about the carry or Cout, now we can draw the K-map for Cout as well, but if you look at here, easily we can write the expression. So let's say this is A bar B C n, A bar B C n, because we are getting 1 here. So I'm writing A bar B C n, right? For next position, so this we have considered because this is also 1. So here A B bar C n. So we can write A B bar C n, right? The third one which we are having here, we write A B C n bar. So we can write A B C n bar. And the fourth one which we are having here, we write A B C n. So we can write A B C n. Now if we solve this, here C n we can take as common. So out of these two terms, this one as well as this one, we can write A bar B plus A B bar C n, right? Plus here, if we take AB common from here, we will write AB C n bar plus C n. So this C n bar plus C n will give us 1 only, and A bar B plus AB bar, this is the Boolean expression of A XOR B. So A XOR B ending with Cn plus AB. You do remember This is the Boolean expression of C out. So I'm highlighting here the Boolean expression. So this is the Boolean expression or carry output or C out, output carry. And this is the Boolean expression for sum. Right? Now we can draw the circuit for this. So there are multiple ways we can draw it. Right? So we can draw XOR and then let me draw it. So let's say we move on. So I'll draw here. Let's say I'm having A. So this is my A. Okay. And keep, and let's say there is B input and I am taking C in as well. So these three are the lines. Now we can take the bar of them. So I'm writing this is A, this is B, and this is C in case we are having. Okay. Now let's take the bar of them. So A bar I'm taking here like this. Okay. So let's say there is a NOT gate. And here we are having the bar of A. Similarly, we can have the NOT gate here. We can have B bar here. Like this. Same thing we can do for C in also. So whenever we require C in bar, we can get. Let's say here as well, we are getting complemented form of all these three. So this is the C in complement. Right? Now when we want to get sum is the XOR of A, B, and C. So that is not very difficult. So XOR we can draw here like this is, so we are having XOR, right? We assume that this is one of the XOR. Either you can take 3 input XOR, okay, or if it is 2 input, then the output you will pass to the another, right? So if you consider this as 3 input XOR, then it will give you another diagram. So let's say I'm passing this A, it is going like this, like this, and we are connecting, right? So this is A. Now when B is coming to this, B is this, so B is getting connected like this. We can connect it, and here we'll be getting A XOR B, and this thing we can pass to other XOR with C. So let's say C is coming from here like this, and we can draw another XOR here. So here we will get A XOR B XOR, right? Now if you want to draw, so this is the sum actually. I'm writing here sum. For carry, if you look at, this is A XOR B dot Cn and A and B. Okay, so A XOR B is here, we can take from here and we can perform ANDing with this. So what we can do from here, we get this thing, you can take it from here, let's say like this, it is coming down, and this is A XOR B, and along with A XOR B we perform ANDing with Cin. So Cin is coming from here, let's say this is Cin, oh no, it is Cin not, Cin is here. So Cin is coming from here, and there is AND gate, so we perform the ANDing here. So we will get here A XOR B ANDing with Cin, right? Along with this we need AB. So AB we can get here, let's say A is this, we can pass this A like this, so this is A, this is A. Similarly we can get B from here, this is B, can come like this, and we can get B here, and for ANDing we apply one AND gate here, so we will get here A and B. Now we need to apply one OR gate, so let's say here we are applying an OR gate so that we can get, so there's an OR gate, so here we will get A XOR B Cn or A dot B. So this is the carry or C out. This is C out, right? So this is full adder. With this, I'm closing this lecture. Thank you, everyone.